Absolutely. I'm going to explain the assessment of obstacles impact. This is part of a European project, LIFE project, involving Liège University, I represent, and we collaborated with Namur University and Wallon University. I am going to present today the assessment in 6 parts. I'll show you the background, locations, the BOC, watershed, the assessment of transverse works on sediments transport and on hydromorphology, and I'm going to show the assessment of a dam removal and small wear, and another more significant project. So we'll talk about the rough ramp removal. So we work within the context of the Water Framework Directive. So we'll talk about the sediments today. The sediments at the bottom, coarse sediments at the bottom of the water bed, which are, of course, significant elements of the ecosystem life. They are the substrate on which different organisms can live. So we won't necessarily talk about self-cleaning. But of course it is part of its role. So here are the type of works, the dams that can impact the sediments transport. So we have shown here the land balance. We can see the balance between the flow rate, the slope, the quantity and size of the sediments. So if we have a high characteristic, a disturbed conditions with a dam, for example, then there will be an imbalance in the bed load. With here, you can see degradation upstream of the water retention with bank erosion, for example. So this is just a bit of background. Here is a map of the area we worked on. It represents 237 square kilometers. We have the right bank affluent of the Meuse, and we have the Chaux nuclear power plant, and here is the area more specifically we worked on. We are in Condre. This is the geological map with a lime scale. With the flow of the river coming mostly from groundwater. That's why a lot of mills and industries, plants were built on this stream. So here are the characteristics. With Emptinal, Spontin, Bauche, so there is a strong slope at the top, a lesser slope, the base level. And we worked more specifically on the Spontin area downstream. You can see here the characteristics of this section. The river Boc is quite powerful, as you can see. It can transport coarse sediment between 4 centimeters and 90. We have 76 barriers on this section, which we have distributed and color-coded, with the green being the minor obstacles, and the dotted green line, the long sections without obstacles. you can see the obstacles for the fishes and the sediments. That's about one obstacle every 1.8 kilometers. So they're mostly small wells between 1 meter and 3 meter high. They can be fixed here, you can see on the top left-hand side picture, or they can be mobile, as you can see on the bottom picture. They can be made of metal. The one on the right-hand side can be an obstacle for the sediments, but not necessarily for the fishes. So what about the assessment itself? After we read up the scientific papers, we found different hypotheses. The first one is that the bed load is trapped upstream of the dam. Second, only the bigger elements are trapped, so we can talk about total major trap or partial trap. We can say the bed load manages to get through to the downstream. We talk about transparency, or we can say it's transferred by the bottom valves, and we talk about transparency here again. So how do we assess the impacts? The protocol, which I'm going to explain now, was first describing the obstacle, the barrier. Is it fixed or mobile? And what are the mobile parts then? How much does it fill in? How much does it spill out? It can show in this case that, for example, the bed load can go through this obstacle. And now we have a profile analysis. This is the Bock profile downstream of the Spontin village, with a 70-fold exaggeration to show the characteristics. This is the theoretical characteristics of the riverbed. You can see the 4 arrows representing 3 arrows representing the 3 barriers, and we could assess how much of the sediments is retained. That represents about 700 cubic meters in Chancin, upstream, which takes over several years. Just a few years. It is pretty fast. So we wanted to analyze granulometric parameters as well downstream. So we sampled using the Wallman method. We can see upstream of the obstacle the amounts much more coarse than downstream. So again, we wanted to find out the characteristics of the bed load. So we used 2 types of markings, one of them called microscories. We could find here the different holes dug downstream. We thought possibly products could have been spilled into the river by local industries and could give shape to these type of characteristics. Another element we wanted to do was implement pit tags in the pebbles, looking into the implementation upstream, and then try and analyze the pebbles downstream, see if it was able to go through the obstacle. Here is the types of spillway channels on the left-hand side, and on the right-hand side, the inlet channel for the mill. And we have what we call a valve here in the middle. On here, the right colored is the spillway channel. In pink in this graph, so we had a significant flood and the valve being closed. We were able to find 30% of the pebbles had passed through the obstacle. So there was a partial trap. We found the caused elements only were left upstream of the spillway channel. The valve had been damaged, so we thought the sediments could have gone through. So this is a picture after this significant flood. And we have a smaller flood and analyzed on 21st of September 2014 with the bottom valve open. And we found 72% of the pebbles marked downstream of the dam. They mostly went through the bottom valve, which was open, but also through the crest, because we can find here at the spillway channel level some elements which couldn't go through the bottom valve. So to conclude, we can say that the dams were quickly filled up by coarse sediments, so they let the bed load go through partially. We can say the bed load can easily be transferred through open bottom valves and a low level of incision downstream of the barriers. So we're able to map microhabitats and calculate the morphodynamic attractivity indicator. They were presented in the previous conference. So this is an example of Boc à Spontin, small spillway channel, about 1 meter high. We worked on upstream station and downstream station. Upstream of the barrier, we saw low level of disturbance. Granulometric characteristics were more or less equal to the reference characteristics. And the river downstream show lentic flow, so low level of disturbance. So as we said, the flow was at low rate and mineral substrates with high levels of silting. So the morphodynamic attractivity indicator showed a level of 22%, which was quite low compared to the reference station. It was 75%. 22% upstream, close to 70% downstream. So it was quite a good result. So we're able to condition about 22 obstacles to enable the fishes to go through with different scenarios. And this is the remaining obstacles. As you can see, we were able to work quite a lot on the Meuse River, and in the intermediate area, there are 31 kilometers linear river open. So to give you a bit more information on the conclusions, this is, as we said, the Spontin spillway on the Boc. I'm going to tell you about the geomorphological aspects, mostly. So here are a few pictures of the leveling, removal of the obstacle. I'm going to tell you about the sediments tagging But first, the comparison of the upstream and downstream stations. So this is all maybe a bit more complicated, but basically we wanted to show that the topography characteristics showed the changes, looking upstream at the progressive erosion, which could spread to the banks and local population housing. And after we removed the obstacle, we saw sediments leveling. And the significant actions were these actions, and we actually had a very significant flood right after our obstacle removal. So it was a very significant time. So we then drew digital models before obstacle removal and after obstacle removal. So we were able to see the parts suffering from erosion. This is upstream. And so we think we've got a balance of 90 cubic meters. That's an erosion of 19 centimeters. And we did the same exercise downstream. Here are the results on the right-hand side. And we see a positive result. That's an accumulation of 60 cubic meters. So overall, the general balance is 29 cubic meters deposit. We suppose they are downstream of the 100 meters because we don't know where this difference comes from. And we looked at the bed load tagged, the pit tags, which we were able to trace 340 meters downstream of the injection. So it goes quite far. And another example I wanted to mention, the rough ramp example, as you can see on the left-hand side, with a concrete bank, 600 meters long channel. It was an obstacle for the fishes because we had a strong, high flow rate, even in low-level times. And to help for fishes to be able to go through, we couldn't widen up the banks. That was not a possibility. But we wanted to increase coarseness to help. So on the right-hand side, that's before rehabilitation, and on the left-hand side, after rehabilitation. So aquatic habitats were created. Some blocks and spawning areas created in this area mostly for trouts. So then we were wondering if these elements can really be in use by that stream. We wanted to calculate the competencies. So we looked in the field, injected pit tags, again, the same ones we were talking about earlier. And the second approach was quite a classic approach, which calculated using transport formula, looking at the diameter of the elements and the shearing load. So we saw that with the Manning coefficient, that coarseness was increased. So we now assessed flooding risk every 4 to 5 years, following our calculations, and elements close to 11 centimeters can go through, whereas 30 centimeters blocks could be transported. So we think that the spawning areas have a limited duration because of their dimension. They are too large, so we're going to be moving them downstream. So the conclusions of our assessment are that the barriers on the Bok River are generally transparent apart from a few cases. The leveling option is the most efficient. It helps in the free movement of the fishes. It helps in reducing the waterline upstream, less floods. We can restore lotic flow for mostly salmons and supply coarse sediments downstream for potential spawning grounds. As I said, we have mitigated opinion with the rough ramp situation because of the impacts I already mentioned. Thank you so much.